Tonight's topic is probably the most difficult topic we'll be talking to in this one-year creation program. And the reason being is multifold, actually. One, the actual substance of the subject matter requires an extremely mature mathematical background, which we won't be touching tonight. Although there will be a few algebraic equations, we won't do too much of that. The second thing is this is the weakest area in the creation model. A lot of research has been going on of recent times, but still we have so much work to do in this area that there's just a lot to do. So let's continue. And what we want to talk about tonight, we're going to look at the definitions of what we mean by the terms cosmogony and cosmology. And if this is the only thing we get out of this evening's presentation, it will be worth not spending time out in the wonderful sun tonight. We'll define what the problem of starlight and time is. And then what I'd like to do is provide a very brief history of the various creation cosmologies, or cosmogonies, depending on how you want to view things, that creationists have proposed over the years. Then we'll look at the modern models. Then I have a few comments on the nature of space-time as a result of especially the modern models that have been offered. And then the issue of where do we go from here. So these are some of the things we want to talk about tonight. So let's take a look at the difference between the terms cosmology and cosmogony. Both words are derived from three Greek words. It may be difficult to see, but the first Greek word that goes into both of these words is the Greek word cosmos. And I want us to understand what this word means, because we've heard of Carl Sagan's usage of the word, his book called Cosmos or Cosmos. But it's actually a Greek word that means an arrangement. But in its real esoteric or its essence sense, it means an orderly arrangement. And the emphasis on the word by itself, the etymology of the word the emphasis of the word is on orderly, not arrangement. It's a qualitative word, not a quantitative word. And as we go through and study cosmology, it becomes very apparent that that's the better meaning, and that's the way we should understand it. The next word is our famous word logos, and this word means dynamic word or message, or in some of the translations, study of. And then finally the word ginomai, which means become, born, begotten. So that cosmogony is a compound word between cosmos and ginomai, which means to become. So we're talking about the becoming of this orderly arrangement that we're calling the cosmos. So cosmogony, in its true sense, means the study of how the universe originated, not how it operates. Cosmology is specifically the term that we want to use to study how the universe operates. And it's important that we recognize the distinctions in these terms. They're very important distinctions because, to be perfectly honest, what we're talking about tonight is mostly cosmogony, not cosmology. If you and I were in our laboratories and we were dropping balls and observing how they fell, took measurements, and we tried to come up with a physical law for that motion, that would be cosmology. We're studying how the universe operates, how it behaves. But if we're talking about how the universe came into existence, we're talking about cosmogony. Let me make one further comment on this page. There's another term that we use for cosmogony or cosmology, or cosmos actually, and that word is universe. And that word actually gives more information about this place that we live in than the word cosmos. The universe is also a compound word, but it's a compound word between diversity and unity. So the cosmos, from a Western science perspective, is a unified diversity. It's a Trinitarian concept. Okay? No other worldview, if you will, can claim to view the world or the cosmos in a Trinitarian way. So it's important that we recognize and bring in this discussion of Trinity. So there are the distinctions between the two words. Let's take a look at the starlight and time problem. And to have a good understanding of this, we need to understand how big the universe is. But because it is so big, we need to come up with a new measuring unit. If we're going to measure the distance, the size of the universe in feet, then we're going to have huge numbers, and they're very difficult to deal with. So what we do is we'll take a light year, and a light year is nothing more than the distance light travels in a vacuum in 1 year, 365 days. Well, the value of that, of a light year, is actually 5.8 trillion miles, or 9.5 trillion kilometers. So that's a pretty big unit. So when you talk about an object, a stellar object that's, let's say, 1,000 light years away, or we'll look at one tonight, 6,500 light years away, you take your 6,500 multiplied by 5.8 trillion, and that will give you the number of light year, or the number of miles that that object is away from the Earth. So the light year is a fairly large distance, but it's not large enough. The parsec. Has anybody ever heard of the term parsec? Well, the parsec is related to a light year by a multiplier, but that's not how it's derived. A parsec is essentially the distance of an object when that object subtends a 1 parallax arc second. Now, how's that for a wonderful definition? What do we mean? Okay. I'll take the cursor over to your screen. And here's the object we're trying to derive a distance. And let's say that happens, well, that's the Andromeda Galaxy. But let's say that this is the object that we're trying to measure its distance. And an arc second is literally, you take a degree, a circle is made up of 360 degrees, and you take one of those degrees, divide it by 60, that gives you an arc minute. Take that arc minute, divide it by another 60, and you get an arc second. So you have this teeny tiny angle, okay? And that's what this angle is, 1 arc second, and the adjacent side is the distance between the sun and the earth, and that's called an astronomical unit, 1 astronomical unit. Okay? So, a parsec is the distance of an object that subtends 1 astronomical unit. And it happens to be, let me bring my cursor back over. And it happens to be, therefore, 3.26 light years. So 1 parsec is 3.26 light years. Okay, that's the distance. So if the object we're looking at is 50 parsecs away, you take 50 multiplied by 3.26, and that will give you the number of light years that it's distant from the Earth. Now, parsec really is not a big enough unit either. So we use kiloparsec, megaparsec, gigaparsec, and so on. So the object is the universe is very big, and these measuring units help us understand things in a little bit better way. So 1 parsec is 19 trillion miles. So it's a very big universe. And the Hubble telescope has greatly expanded our universal observational universe. Due to the Hubble, we can see much further because we're beyond the atmosphere of the Earth, and the light that's coming into the telescope is not disturbed, so we can see much further into the universe. So it's expanded our observable universe by definition. Now, the latest, this is interesting, the latest estimate of the diameter of the universe is 28 billion parsecs. Now, if you read some articles, they may say, well, it's only 14 billion light years. But that's based on some confusing terminology. So the actual universe is 28 billion parsecs, which is 93 billion light years. So the universe, if the universe is only 6,000 years old, no object greater in distance than 6,000 light years could be observed today. So this is by definition what the problem of the starlight time issue is. Any object greater than the age of the Earth universe, beyond which the biblical text demands, which is roughly 6,000 years, the question then is, how did the light get here? The Andromeda Galaxy is over 2 million light years away. How did the light get here from the Andromeda Galaxy? So this is a legitimate problem for the scientific model of creation. So, let's take a look at some of the historical cosmologies that have been offered. And in each of these cosmologies, they're not addressing a full-blown cosmological view. Typically, they're only viewing certain problems, like the starlight time problem or the so-called red shift problem. So they very often are only dealing with one particular problem in astrophysics. So let's take a look first at the tired light model. This is an interesting model and has fallen out of favor for some time now. And what the tired light model is that light slows down due to cosmic friction. So when you shine your flashlight, if you were to follow that segment of light, if you could go right with it, and you would notice that your light over time slows down. Your light beam slows down. And it would be due to the photons interacting with the cosmic fabric, if you will. And so you would see this light slow down. The reason why this was invented was to address the issue of the red shift. The further objects are away from the Earth, the greater the red shift of the object. And what I mean by red shift is, as the light comes to the Earth, the spectrum of that object is shifted toward the red spectrum. Okay? So the light that would be normally yellow is a little bit more orange. Okay? That type of thing. So here's our little photon. And he moved much more quickly than I wanted him to, but that's because my computer is so slow, the processor has just about had it. So this modeling follows the traditional exponential decay law that we show here. So the light, when the photon of light is first given off, he's at a high speed, and then as he travels through space, he gets smaller and smaller. And this little r value here is essentially a measure of the resistance of this cosmic fabric that the light is traveling on. Okay, and so this was a model that was used to describe the red shift. It's now since fallen out of favor, and we'll show why. First of all, the tired light model addresses mainly the red shift problem. If the thing was true, if the tired light model was true, then every stellar object would appear to be blurred. And the reason for that is because if the speed of light is slowing down, the momentum of that photon is changing. Okay, so what that would happen in your eyeball is you would start seeing this object to be in a blurred manner, because the momentum at each point in space is different. And so to your eye, that would be accounted for as a blur. Well, there's not one object up there that's blurred due to the tired light model. So it's obviously not a proper view. There's no known mechanism. We can say that it's friction with the cosmic fabric, but what cosmic fabric? It doesn't predict the time dilation that we know is true. For an example, when muons come in from the upper atmosphere, they experience time dilation. And so this doesn't explain that. It does not explain the 3-degree Kelvin background radiation, which every cosmology ought to. And so as a result of these problems, this tired light model is no longer in vogue. Now, let's take a look at the C-Decay model, which probably many of us are familiar with. And this is I'll say partial cosmology that was formulated initially by Barry Setterfield out of Australia. He published a series of articles in Ex Nihilo in the late 1970s, and then he published actually a rather interesting collection of his articles in 1983, and then later on in the 80s he published a technical monograph to the Stanford Research Institute through Lambert Dolphin, and so this is how he has formulated and popularized his vision of the decay of the speed of light. The fundamental model here that Setterfield has done, the fundamental research that he did, was based on collecting the data over time of scientists who measured the speed of light. And he took that data and he attempted to come up with a curve that fit the data. This is called curve fitting. And he started with the data that Remer generated in the mid-1600s, all the way down to the latest techniques of interferometry and ferrometry and so on. And he came up with a very interesting model. Here's the data. I apologize if that's a little bit small, but you can see here that the data here shows a slight increase in the mid-1600s, and this is the data that Remer derived through looking at by looking at the moon as not the Earth's moon, but one of Jupiter's moons, as it went behind Jupiter and came back. He could measure the time when the moon went behind Jupiter, measure it when it came back, and then from that he could calculate the speed of light. Okay? So from this set of data, he came up with a very interesting curve. And this is the curve here. Now, it's called a cosecant squared curve, which we'll explain here in just a minute. This will be the most technical of the equations we show tonight. So, and here it is here. If you notice, the curve itself, it starts from a very high point in the beginning. And this is the cosecant squared term. So it has a very high initial value, and it very quickly drops off and levels off very quickly. Now, what's interesting about this is that when you perform this curve fitting analysis, it looks like the curve leveled off around 1967 or sometime in the mid-60s, which is unfortunate. It's very unfortunate because now, no matter what we try to measure the speed of light, we're going to get the same value that we got yesterday or tomorrow. So there's an inherent problem with the way the model is formulated. Okay? So I'm going to argue that if the speed of light is decaying, we cannot show it by actually looking at the data. Okay? And there's some other reasons why that's true as well. So it's somewhat unfortunate. Now, what's interesting about the cosecant squared term equation is that this is very closely related to certain processes that go on in stars. They also follow a cosecant squared term. Is there anything else I need to discuss on this particular equation? Not necessarily. Okay. Now, the other thing that Setterfield mentioned, if the speed of light is in fact decaying, there are other physical constants that are related to this decay, which we'll look at. The electron rest mass. When an electron is just sitting there, doing nothing, there's an equation E is equal to mc squared. That is very familiar to us all. Now let's take a look at that equation. E is equal to mc squared. E has to remain constant because of the conservation of energy, right? It can't change. So if C is changing, what must M be doing? M must also change in an inverse way that C squared is changing. So that means that M has to be proportional to 1 over C squared in order to keep E constant. Okay, so that's one of Setterfield's predictions, is that the electron rest mass is proportional to 1 over C squared. What does that mean? That means in the past, when C was greater, M was much less. That has major ramifications. How about Planck's constant? Now, what is Planck's constant? It's probably one of the most important physical constants that we could discuss. It's the constant that describes the energy of a photon. It's a very small number. And here it is here. E is equal to h nu, where nu is the frequency of the photon. But the frequency is also equal to the speed of light divided by the wavelength of the photon. Okay? So hc over lambda. Now lambda has to remain constant. So what does that mean? If the energy has to remain constant and lambda has to remain constant, but that C is changing, that means that H must change in an inverse relationship of C. So H is proportional to 1 over C squared. Now let's take a look at one more, and this is the important one, and that's the gravitational constant. Now we're all probably familiar with this famous equation, F is equal to G times M over R squared. That's the force generated between two gravimetric objects. If you take the mass of the Earth and the mass of the Sun, the mass of the Earth and the mass of the Moon, you take their masses, multiply them together, divide by the distance between them, or the radius of the distance between them, and multiply by G, you'll get the force between those two gravimetric bodies. But we said that mass, look up here, in the first one we said that the mass was proportional to 1 over C squared. So if we take that, substitute it in for the two M's, we get then that G, if R is constant, if we keep these two objects in the same distance, then we find that in order for the force to remain constant, G must be proportional 1 over C to the fourth. Okay. Very interesting. And then we'll just make a quick note about the radioactive decay constant, and that would mean lambda, which is the radioactive decay constant, is proportional to C. What that means is if C was greater in the past, so was the decay constant, which means the radioactivity in the past was greater. Okay? So let me say this about the C-Decay model. There are many researchers, both creationists and non-creationists, that are looking in other areas of research that are claiming very similar arguments that the speed of light was greater in the past, or that the speed of light being greater in the past explains certain phenomena. And of course, creationists, particularly the rate group, is using this idea in forming many of their submodels within the creation model. Okay, what's the problem and the strengths of the C-Decay model? Well, according to some, it lacks a rigorous data analysis, and I believe that to be true. The latest research over Remmer's data shows that it's essentially equal to today's value when you look at the error bars and so on. So I don't think that if the speed of light is in fact decaying, that we can look at the data that we have over the time that we have it for and conclude that. I'm not saying it's not decaying, I'm just simply saying we need another approach to show it. Now, it could also lead to a local violation of the conservation of energy. In that 1983 monograph, Setterfield has a derivation of the energy density based on the decay of the speed of light, and unfortunately, it varies. Okay, so if you take a unit volume of the universe and just take that as if it was what was going in is the same coming out, it turns out that it's actually not. So what's going in is different than what's coming out. That violates the first law. So we need to look at that. It lacks a rigorous mechanism. Why is the speed of light decaying? He doesn't offer any general relativistic model per se, although he could, but it lacks a rigorous mechanism. Implications, however, agree with other researchers from other fields. The rate group is claiming that the permittivity of free space has changed, and you can show that that's directly related to a change in C. So there are some implications here. And then finally, it addresses the starlight and time problem and potentially the red shifting of stellar objects. So there are some strengths, there are some weaknesses, and so that's where we are with Setterfield's model. All right, there's another model that's called the Riemannian space model. Has anyone ever heard of the famous mathematician Riemann? Great, one of the greatest mathematicians of all time, a student of... he was in the pedigree of Friedrich Gauss. But Riemann looked at non-Euclidean geometries. And what I mean by that is geometries where parallel lines meet at infinity. See, in Euclidean space, parallel lines never meet. But in Riemannian space, parallel lines meet. I'll give you a good example. The kids out there tonight were playing basketball, and they had a ball. And that ball had your typical yellow and orange stripes on it. But what's interesting is, if you take two people and you put them at the bottom of the ball and say, walk towards the top, and one goes this way and the other goes that way, what happens? They run two parallel paths that happen to meet up at the center. Okay? That's a non-Euclidean geometry. Okay, so it's a Riemannian geometry. So this is what is being meant when they say parallel lines meet at infinity. Well, I'm not going to spend too much time on this, but in the early 50s, two scientists by the name of Moon and Spence, not creationists, came up with this model, and they claimed that if we use a Riemannian geometry for the universe, then light from everywhere in the universe can get to us within 16 years. 15.71 to be exact. Well, in 1983, in the Creation Research Society Quarterly, Russell Ackridge wrote a wonderful refutation to that because a lot of creationists were considering using this as a potential model to solve the starlight time problem. But Ackridge did such a wonderful job that I don't know of anyone who is using that particular model. Not that we shouldn't be using Riemannian models. I think that's the way to go. But this particular model required the mass density of the universe to be so great that it just wouldn't work out. All right, the next model that we want to look at is the appearance of age model. And for us here, this is an important model to discuss because we've all heard it, I'm sure. Okay, well, God created the universe to appear old, to appear mature. And it's reasonable to say that because the universe has to operate, right? It has to be mature in the sense that the Earth-Moon system is functioning properly. So he's not going to create it as if the universe is a child and has yet to grow. Okay, so he's going to create it in a mature fashion. So, God created the universe to look old or mature. So, let's address this issue. Let's take it systematically and start asking ourselves some questions. Suppose you and I happen to transport ourselves back to the Garden of Eden. And we go to Adam and say, Adam, how old are you? And we happen to land our time craft on day 10. Okay, so Adam's been around for what? 4 days. He's actually 4 days old. And you ask Adam, how old are you? Well, he looks at himself, he says, well, I'm in pretty good shape. I must be 25 years old. And, you wouldn't argue with him. But is that really how old he is? No, he's only 4 days old. And yet he looks mature, and he could help you do your arithmetic probably. Well, let's suppose you grab the nearest palm tree, sleep overnight, day 11 rolls around, and you ask Adam, how old is that 100-foot oak tree that's nearby. And there we go. After counting the rings, once you cut the tree down, you count the rings and you say, well, it's about 60 years old. But how old is that tree? Well, 11 minus 3, right? Well, we're on day 11, and it was created on the third day. So it's 8 days old. But yet, you count the rings, it's 60 years old. 3 days older than Adam, that's right. So, we're starting to see some issues here. Now you ask the question, okay, I'm looking up at the stars, how old is the Andromeda Galaxy? Well, it's about 2.5 million light years away, so it must be 2.5 million years old. So now you can see the problem in a big way. The appearance of age model breaks down after 6,000 years. Okay? So if you know the actual age of something, and the process by which you are measuring its age says something different, you know that measurement, that mechanism that you're using is false, is broken down. Because it even broke down if you ask Adam how old he is, or the tree. Okay, because you know how old the tree is. So the appearance age, as far as astronomical items are concerned, only works for items that are less than, let's say, 6,000 light years away, because that's how old the Earth is from a biblical perspective. Now, it's also even worse than that. The appearance of light art model produces fantasy events. Now, what do I mean by that? This is an interesting problem. It's an interesting problem in philosophy, actually. Now, I want you to follow along here. That is the Crab Nebula. The Crab Nebula is a nebula that formed in 1054 AD. That's when man observed this thing to poof, start exploding. Okay? So that's about 5,000 years after the creation of the universe, okay, from Earth's perspective. Okay, so let's say the Earth is created, or the universe is here. 5,000 years later, we see this Crab Nebula come into view. Okay, so what do you expect? Well, you would expect that 5,000 years ago, this thing exploded, and finally the light of that explosion is reaching Earth, and that's what we see, right? That's a right assessment, right? There's a problem with that. The distance of the Crab Nebula is 6,500 light years away. So there's a 1,500 light year shortfall. So what does that mean philosophically? That means that of this light segment, let's say here's the Crab Nebula, thing explodes, and that light of the explosion hits Earth. There are 1,500 light years worth of light segment that's a myth. Okay? You see that? So the event never took place, but it's recorded in the light. So what that means is God created a fictitious event, and this light in transit gives us this information. So it's also sometimes called the light in transit model, where God created not only the object, but the light in transit. But this particular thing was a mythical explosion because it took place 1,500 years off. Okay? So it's a real problem for the appearance of age when it looks at astronomical data. But I want to emphasize that the appearance of age is a proper way of viewing things when the context is well understood. So the interesting thing about the Crab Nebula is it must never have happened. But we know that it did. So we have to look at another solution for this problem. All right. All right, let's take a look. Yeah. Yeah, that's the issue about the mythical event. Okay, let's take a look at the Humphreys model. And I'd ask you to put your thinking caps on, because I'm going to go through this relatively quickly. And what I've tried to do is simplify it graphically. I don't think I have any equations in this particular segment here. Too often we think of time and space as separate entities, that you have space here and time here, and never the two shall meet. Well, that's not quite the way modern physics views the universe. Modern physics views them as parts of a unified whole, and we call that space-time. And to illustrate this concept, consider a trampoline, a famous trampoline. Now, if you look at this gal that's on the trampoline, notice where her feet are. Her feet are touching the trampoline, and the mass of her body is pushing the trampoline down. Okay, so it's actually warping the fabric of the trampoline. So if you consider, let's call it a two-dimensional object for a minute, a two-dimensional surface, being warped into the third dimension. We're talking about 4 dimensions now. So when we talk about space warp, we're talking about space being warped into time, the 4th dimension, and so on, things of that nature. So we want to think of gravity no longer as an inherent force between objects, but gravity now is the warping of space. So the more mass of the object, the more bending space will be, the steeper the space curve will be, if you will, and that translates into a heavier gravity field. So if you're on the Earth, you have 9.8 meters per second squared worth of gravity slope in space-time. If you're on Jupiter, you have a lot more than that. If you're on the Sun, you have a lot more than that as well. So depending on how much mass is bending space, that determines how much gravity you experience. Okay. So the idea then is that mass bends space-time. And that's the modern view of gravity. It's no longer an inherent force of mass, but rather it's actually the amount of warping of space-time by the mass. Very, very ingenious way of thinking about things, actually, considering where Einstein came from. Okay, Russ developed his model in the early 90s and published it in a book called Starlight and Time by Master Books in 1994. He presupposed that God created the universe through the means of a white hole model. A white hole is the opposite of a black hole. A black hole is a massive object where the mass is so condensed that nothing can escape it. The gravity curve is so great that light itself can't escape. Okay, that's a black hole. Everything falls into a black hole. A white hole is the opposite. Everything shoots out, so to speak. So you have this white hole in creation, and God is spewing forth His wonderful creation through this mechanism of a white hole. So that's basically Russ's model, and it's also Harnet's model. The weaknesses in the original model were that the wrong time coordinates were used, and also the sign changes from time to space and vice versa were missed. For you technical geeks out there, there's a thing called an eigenvalue. And an eigenvalue can be plus or minus. When it's one sign, it's measuring time. When it translates to another sign, namely goes negative, it's measuring distance. Okay? And the cosmologist has to be aware as he's traveling toward that black hole what value his sign is on his little eigenvalue. And that was a problem here. The strengths, I think, are twofold. One, Russ used general relativity to create his model. And two, he is very committed to a normative reading of the Genesis text and to the entire biblical text. And I think any problems that might come about by the scientific model can be actually, I think, solved by re-examining the biblical model in a normative way and helping to solve any of those problems. Okay, what we want to look at tonight is the latest Humphreys model in some areas. So I'm not going to be talking about the entire model simply because of time. It's based on Genesis 1:3, where the entire mass of the universe was in the form of a sphere of water, and we'll say this water, the sphere, was of radius r, within space-time. And if you recall, Genesis 1 talks about the waters, God separating the waters from the waters above from the waters below. And here we have a look. Now, if you imagine this little saucer or dish-like element, imagine what this is the little r is the radius of the entire space-time. Okay? And God places this water, which is not equal to r, little r, but it's all concentrated in the center of the universe. So it would bend our little trampoline saucer here in this form. Okay? So the arrow right here, the arrow. Let's see, can I get that? Yeah. Let's see, how do I want to do that? I guess I can't. Oh, maybe I can do it here. This arrow right here, that's little r, that's the size of the universe. Then this right here is the waters above. Okay? So the waters above does not take into consideration it doesn't cover the entire universe, but a part of it in the center. And it's bending the universal trampoline in this fashion that we're showing here. Okay? Now, the depth of the well is the gravitational potential energy. Okay, the sides of the well, the slanting of the sides, is the gravity that you and I would experience, just like we saw on the trampoline before. Okay. Now, God began to separate the waters, and this is interesting. For the earth, they are the waters below, and for the universe, for the universal ring, as we'll call it, the waters above. Okay? We've seen this in other presentations. So now you can see this trampoline where in the center, that's not shown here, is the water that God is going to create the earth out of. And then the waters above that he's calling, he's separating these out. Okay? And so, as you can see, the radius of the waters, which is big R, here's the radius, here's the radius of the universe is here, of space-time, and as God separates the waters out, it's getting closer and closer to little r. Okay? So what is happening, in effect? As you kind of disperse the water out through the cosmic space-time, what's happening? The gravitational well is coming up. Okay? So the bottom here, as that water is spread out, is coming up. So, there we go. What a shame. So as the water is spread out towards little r, the bottom of space-time is going to come up. Well, what does that mean? That means the deeper you are in the well, the slower your clocks will tick. Okay? The more you get up to where you have a flat space-time, the faster your clocks will tick. Well, it just so happens that there happens to be a critical mass that if there's any more than that, the trampoline, the universal trampoline, will go below time is equal to 0. So your clocks stop ticking. Time comes to a halt. Twilight zone. Okay? Clocks will come to a stop. Okay? Well, how does Russ tie this in to Genesis? Well, here's how he does it. Now remember, in the center we have the water, the mass of the earth, and then we have this watery ring that God is moving out. Okay? On the fourth day, God creates the stars. Okay? What Russ does in his model, he implies that this is a separate creation of stuff, distinct from the waters that he created in day one. Okay? So the stuff that God created the fourth day stars out of was a separate material creation. Okay? Now the reason why he needs that is because this extra mass would put our trampoline, part of the trampoline, below the critical point potential. So everything that's below the critical potential line, the clocks stop. So nothing moves. Time comes to a halt. Clocks stop ticking. Okay? Now, as God continued to spread out the watery ring, this our universal trampoline then rebounds and comes back up above the critical potential. Okay? So now what happens? Things way out there that God created start ticking. The stars start shining. Okay? Well, what's out there? There are stars. Okay? There are stars out in this region. So as this is coming up, this part now comes above the critical potential line. Their clocks start ticking, and they start shining in all directions. So you start shining here, and this is where the Earth is, right? So as this comes up, all these stars start shining in all directions. So by the time the Earth pops up above this critical potential line, what is there to meet the Earth? The light from every object in space. Okay, so that's how Russ solves the starlight time problem. Because as the stars are throwing their light towards the Earth, there's not 1 second ticking off the Earth clock. Why? Because it's below the critical potential line. Okay? He calls that the achronos region. Okay, much of this was published in the Journal of Creation, and there are 2 websites. I don't have it in this particular presentation. When I send the presentation to the website, I'm going to update it with all the references you might find interesting. Creation Ministries International. It's creation.com, www.creation.com. They have some wonderful papers there. That's a wonderful website. And you also want to go to Answers in Genesis and their reference, their journal, and they have some wonderful papers there. They're all published and free online. They are 2 wonderful websites. This is where Russ has detailed much of his latest research. Now, there's a strength in his model that he's using general relativity. But I have some questions. And the questions actually are not non-technical right now. Is the mass from the fourth day, stars, a separate creation? In other words, are those stars created out of stuff that is not part of the watery ring? My own cosmology maintains as God moved the waters out of the universe, He used mass from that ring to create the stars and galaxies. Okay, that's my own cosmology that I gather from the biblical text. Russ wants to claim that it's a separate creation, which we could discuss. Is achronicity valid from a biblical point of view? In other words, did the clock stop ticking and then come back? Is there something in the biblical text that would not allow us to say that? Is the mathematical physics correct? So these are some questions that we would want to ask from Russ's model. All right. There's another model from John Harnett, which we won't talk about tonight simply because we don't have time. But John Harnett is an Australian physicist who has come up with a model similar to Russ's. It is I'll say, I won't say a geocentric model, but it's a model like the Humphreys model, where the Earth is somewhere near the center of the universe. Okay? All right, let's take a quick look at the nature of space-time. What is the criteria from a biblical point of view for an astroscience submodel? On the macroscopic scale, space, from a biblical point of view, space is viewed as a scroll. Many passages of Scripture where it says God rolled out the universe like a scroll. And it can be stretched like a curtain. Well, Russ is certainly using that in his model. Space can be folded and bent like a sheet. Space expanded from a central area. And the other interesting thing from a biblical perspective is space is bounded. That is, it has an edge. On the microscopic scale, and this is something that's my own particular thinking, is that we need to include this because we forget. God uses a simile. He says space is like a scroll. He rolled out the heavens as a scroll. That's a simile. He's using a simile there for a reason, to tell us that it's similar to rolling out a scroll. Well, what is a scroll made up of from a microscopic perspective? If you have papyrus, it's made out of all sorts of, leafy material and that type of thing. So on the microscopic scale, individual fibers makes up the scroll and therefore perhaps the universe. Space is finite, and space is created and therefore not absolute. Many creationists believe that space and time are absolute, and because they believe that, they're falling into, I think, some difficulties in their modeling. Space and time are not absolute. God is the only one that's absolute. Nothing, no created entity is absolute. All right, let's take a look at a time now. Time has an absolute beginning. Time has a duration. Time is quantized, and we know that from 1 Corinthians 15. And there exists a unit of time below which man cannot measure. Time is created and therefore not absolute. Light seems to simply appear. Isn't that interesting when you go through Genesis? There's no statement in Genesis where it explicitly states God created light and let there be light. It simply appears. It's kind of an interesting issue that we need to exegete in a better way. Matter is created and therefore not absolute. On the macroscopic scale, space-time seem to be viewed as a continuum. And because it is, we can use general relativity to model the operation of the universe. And this is where we need to properly define cosmogony from cosmology. Because tonight we mixed the both together, didn't we? On a microscopic scale, space and time seem to be viewed as quantized elements. So quantum mechanics can be used to model the operation of the universe. So what I'm claiming from a creation perspective, for you and I to sit down in our sequestered room, if you will, and come up with a model of creation cosmology, we will use both relativity and quantum mechanics to come up with that model. So, having said all this, where do we go from here? First, I think we need to rigorously define what the biblical cosmological model is. There are so many issues that we need to address from a biblical perspective, and I mean the scientific elements of the cosmology, that I don't think we're in a position yet from a biblical perspective to construct our scientific methods. One example is what we talked about tonight, about are the stars on day 4 made out of separate stuff than the watery ring? We need to encourage young creation geeks to go into physics, specifically relativity and relativity and cosmology. We need to form a creation astroscience cosmology society. We need to create a journal devoted to the development of the creation model of cosmology and cosmogony, and everyone needs to attend ICC 2012. So these are some of the things I think we need to do. There's a lot of work I think, to be honest with you, I believe very few questions are answered from a scientific point of view. I do think there are some questions, however, that are answered. There are many that remain unanswered, and so there's a lot of work to do. So I'm actually excited about this particular area of research the creationists need to dive into, because it's literally virgin territory. There's been a lot of modeling going on, but that's still just the tip of the iceberg, what needs to be done.